All right, everybody, we're going to continue talking about chemistry at the carbon alpha to the carbonyl now. So what I want to start talking to you about is a little bit of information about relevant pKa's. Now you might look at this ketone, and your guess would be looking at, say, this carbon and that proton, and your guess might be something like, well, it looks like an alkane, which means the pKa is going to be about 50. And if there wasn't that carbonyl right next to it, you would be right. However, there is a carbonyl right next to it, so that is not the case. What we have here in this molecule, I'm just going to rewrite it for simplicity's sake, is removing this proton, minus H plus, through a variety of different methods. You now have this, and as we established in the last video, there is a resonance form between that structure and this one. And because of that resonance form, the acidity of that proton is a lot lower than you think it would be. In the case of ketones and aldehydes, we're talking a pKa around 20 to 24. Now, folks, that's less than an alkyne proton. So this resonance form is really what's doing all the work for you in terms of making that pKa so darned low. Now, moving on from this, there's a couple other that we should probably look at. So let's rewrite that over here. The ketone or aldehyde, I'm going with the ketone right now, losing its proton, becoming this. You're at a pKa of, I'm going to say 22, because that's right in the middle. What about an ester? Well, let's take a look at that. This ester, you lose the proton from that carbon. You're looking at this. Now, that molecule has a pKa of about 25, so slightly higher than that of the ketone. All right, what about the amide? Fair question, what about an amide? Well, let's look at the amide. This molecule has a pKa much higher. It comes in around 35. Now, we'll get into why the amide and the ester are higher than the ketone or aldehyde in a little bit, probably in the next video we do. Now, there's a couple more here that I think might be interesting for you to look at. Consider this. All right, this is diethyl malonate. The protons here between those two ester groups, which gives you this structure for its negative charge, this has a pKa of about 13, less than water, I might point out. Now, why would this be so much more stable than the other ester on the previous page, which came in at about 25? The answer to that comes from the fact that you've got two carbonyls through which you can do your resonance. One of them looks like this. Excuse me. One of them looks like this, and then the other one would simply be the exact same basic structure, but you have gone through and resonated through the other carbonyl. So, two forms of resonance, meaning more stable. All right. Couple more I want to throw at you here just because we'll be using them in the future, and that would be what about something like acetonitrile here? Well, if you lose the proton off of this, what you wind up with is this. And that has a pKa of about 25. Now, you might be looking at that and saying, Dr. Weigel, comma space, there is no opportunity for resonance for that anion. To which I say, pshaw, yes there is. And it would look like this. So that is resonant capable. In fact, it is just about the same pKa as a standard ketone or aldehyde. Now, one more I want to throw at you, and that is nitromethane. Now, some of you very, very cleverly threw nitromethane at me on the quiz. And I gotta say, that actually worked really well. It was very clever. I'm impressed with that. So let's figure out what the pKa of nitromethane would be. So the pKa of nitromethane, you will lose the proton, and you're here. The pKa is 10. Which is really, really freaking low. Now, to understand why, we should take a look at the Lewis structure of nitromethane. There's the Lewis structure of nitromethane. We lose a proton, and here's what we have. All right? And you're thinking, well, there's no resonance structure there. And the answer to that is, oh, pshaw, because there is. And it looks like this. There's a heck of a resonance structure there, which accounts for the proton on nitromethane being so low. Okay, so now that we've established all of that, we should start thinking about what bases we can use for enolate chemistry. Okay? Now, there's the ones that everyone always likes to go to, probably because it's the first base that we really do anything with in organic chemistry, which is hydroxide or alkoxide. Both of these, the parent water and alcohol, tend to cruise in with a pKa of roughly 15 to 16. So when you're dealing with something like, say, this ketone, or rather, let's go with an aldehyde this time because I'm feeling a little fun. This is acetaldehyde. Or if you're IUPAC, methanol. Okay, now this proton has a pKa, again, just a real quick reminder, cruising in at about 22. So whenever you use whenever you use, say, acetaldehyde and KOH, what you're going to have in your product mixture is a combination of the enolate, which is the one you wanted, plus some unreacted acetaldehyde. What's the ratio going to be at a given time? Probably slightly favoring the acetaldehyde. So, in situations like this, where you're dealing with an aldehyde or a ketone, sometimes you don't have time or desire to be subtle. Ladies and gentlemen, at this time, you introduce this to the jackhammer, sodium hydride. That is going to give you the enolate at almost 100% conversion. Now, something I want to add here, a couple people made an error like this on their quiz. Notice this proton on the aldehyde is not acidic at all. Does nothing to do with the chemistry that we're talking about right now. So what does is the formation of that anion. Sodium hydride is great. It's the jackhammer. Another one that you can use in every situation to pull that proton off would be LDA. Now, there's a lot of these abbreviations we throw around, so I try to minimize their use. Ladies and gentlemen, this is the structure of LDA. Right there. Lithium, diisopropyl amide. And as you can probably guess from the names, LDA. All right? Folks, this thing is a monster of a base. And what makes it kind of cool is not only is it a very strong base, which means that you are going to form this enolate at about 100% conversion. It is also very sterically hindered. Meaning there's no way that nitrogen is going to be a nucleophile. Now, that's all the time I have for today. I want to come back when we start talking about dicarbonyls. I'm going to talk about why some bases are more appropriate for those than others. But our next step is going to be looking at the formation of the enol, looking at the formation of an enolate, and the type of chemistry that we can do for those. So until then, have a great day.